Greetings, Earth enthusiasts. If you ever wondered about the incredible perspectives our planet has to offer from high above, you're in the right place. I am Dr. Clive Coetzee, and I'm thrilled to be your guide on this captivating journey into the world of remote sensing. Welcome. And please remember to like, subscribe to, and share this video. Thank you.
And the journey continues. So I was working on 3D modeling in QGIS, this video tutorial, last week, what's it, 6 days ago? Yep, 6 days ago. And where we moved that building statistics data set, we exported it into QGIS, and in QGIS, we did some lovely 3D modeling of that data set. So I was planning to continue with that work because in QGIS we then worked with raster data, and I wanted to work a little bit with it in a vector format, in point format. So that was what I was working on and all set. And then one of my good friends emailed me and said, but have you heard of Random Forest Regression? He's trying to do a Random Forest Regression model for his region of interest, for some of the variables. And I thought, that sounds interesting. I haven't done that. I know about Random Forest regarding land use, land cover classification. So that I know how to use that for classification, land use classification. But I've never worked with it in terms of doing a regression. So I did a bit of research, and it seems like there's quite a bit of merit in doing random forest regression because it doesn't assume linearity. So for example, our normal regression that we've done, what was it, some time ago, where was that now? Let's go, that was so long ago. I can't even remember when. When did we do that? Here we go. 57, 58, 59, 60, 61, 62. That was about 4 months ago. We did just on regression equation where we included time, a constant, other variables, etc., etc. But remember, though, our normal regression assumes a linear relationship. And we know most relationships are not linear. So then it started to make sense to me, but that's maybe something that we can work on. So lo and behold, I've done some work on random forest regression. So I'm going to park this for now, the work in QGIS. I'm going to park this now and then just focus on the random forest regression. And here is the regression that I've performed, etc., etc. So let's go for it because I do think it's very interesting. And what I want to do as a follow-up videos, because this one will take a couple of videos itself. Compare the results of our multiple regression and random forest regression in terms of accuracy and usefulness. So let's go with that for now for our journey. And once we've done this, we'll get back to our 3D modeling or work within Excel or in QGIS using our building statistics, building height statistics. Okay, so as always, point number one, import your region of interest. This should be very familiar with you now. I don't think any of you should find this surprising. This is my region of interest. I'm staying somewhere here. That's my place that I stay. So this is called the Berg River municipal area because the Berg River runs through this part at Mouse here in the Atlantic Ocean at Veldrift where I stay. So this is called the West Coast area. Okay, so this is the West Coast of South Africa, located in the Western province of South Africa, and It is a couple of settlements, but mostly agriculture, fisheries, etc., etc. Anyway, that's just a brief history, bit of useless information. Um, okay, so that's always your first, anyway, my first port of call is to load my region of interest. Okay, now you are more than welcome to use your own. Um, you're more than welcome to use your own region of interest, um, etc. So in some of the videos, we showed you how to load your region of interest, and etc. So anyway, you can go and have a look. So that's your first port of call. Then I always start with loading my region of interest. Okay, let's just delete that. Loading your region of interest in your maps, and then center your map according to your region of interest, and then create a clipping function for your region of interest. So that's also standard format. Okay, also standard format. You load your region of interest, you display your region of interest, you center your map around your region of interest, and you create a clipping tool for your region of interest. So that's 4 standard procedures. Then it's a matter of what is your equation? What are your variables that you're going to model? What are the variables that you're going to model? Okay, and that it's totally up to your discretion. But remember, there we use the standard multiple regression method, okay, or methodology. Okay, you have a dependent variable and you have a range of independent variables, 1 to whatever number of variables you want to include as explanatory variables. So that's always standard. Okay, that's always standard. A dependent variable and independent variables. Okay, so in my case, what I've created is I've created a dependent variable which is NDVI. So vegetation, this health and mass of vegetation within my region of interest. So that's my variable of interest. That's my dependent variable. That's the one that I'm looking at or with interest, what I want to model. Okay. And remember, your NDVI is a standard NDVI. You can either generate it yourself or you can simply just use one of the existing NDVI data sets within Earth Engine. So in this case, we use the MODIS one. So if we go to that, remember I just copy this unique identifier. I go to Google Earth, I go to data sets, I click on data sets, I found search, and I copy that unique identifier in my search bar, and I simply just wait for the search results to come up. There is the data set. I left click on the data set. There it is. It's a Terra vegetation index 16 days. So it generates it every 16 days. It's available from 2000 to 2024, meaning last month. And it's 500 meters, so it's fairly high resolution, which is not ideal, but nonetheless, let's go for it. And it's got 2 bands. It's got the NDVI band, it's got the EVI band. Now, NDVI stands for Normalized Difference Vegetation Index, and EV stands for Expanded Vegetation Index. Expanded Vegetation, enhanced vegetation, there it is. Enhanced and Normalized Difference Index. A lot of people say use the EVI, it's a better indicator than the NDI. It is modified slightly and it compensates for a couple of things. I can't remember exactly the details of it, but people suggest that the EVI is much better than the NDVI. But let's keep with the NDVI. Now again, you got a minimum value and you got a maximum value. Now we should know that the NDVI and EVI ranges between -1 and 1. So we'll stick with that color scheme, -1 and 1. In this case, let's go with -2 and 1. So I have to apply a scaling factor. I have to apply a scaling factor. Okay, you'll see there's a scaling factor. There's the scope, there's your color scheme, color palette, etc. etc. Okay, anyway, so that's my dependent variable. That's the one variable of interest. That's the one that I want to model. I want to model vegetation, health, and mass based on a number of variables, not NDVI per se. Okay. So I load my image collection. I select the band, because remember there's multiple bands, so I have to select the band. I select my dates. Now, the dates you'll initially start off with whatever dates you want to. But remember, within your analysis, ideally you should have the same dates. But that's not a train smash, okay? It's not a train smash. But the more data, the better, okay? The more data, the better. Then obviously I clip it. So up to this is still fairly standard. I've got my data set. I select a band within my data set. I select my time period within my data set, and I clip it for my region of interest. Again, that should also be fairly straightforward now. Then I need to scale it. Now, it's totally up to you whether you want to do the scaling or not. I prefer to do the scaling, but that's up to you. You don't have to do the scaling. But I said I like to do the scaling, okay? Because I want to work with the actual numbers. I don't want to, after the time, do the calculations and the changes to the numbers. I prefer to do it up front, so when the result is presented, it's presented in the correct format. But that's a personal preference. Sorry. That's totally a personal preference. That is up to you. Okay, that's your choice. Okay, then obviously, because there's multiple images, I generate a mean image. Now again, we can play around with mean or median. We can play around with mean or median. I prefer the median. Okay, but again, we'll have to generate the results and then see if we use the mean versus the median, whether our results worsens or improves. Okay, so for now, let's stick with the mean. Okay, we'll come back to that. We can change that at a later time and to see whether it's going to be a mean or a median value. Then I'm going to rename it NDVI, so meaning the band. So once I've done everything, I scaled it, generate a single image, which is a mean image, etc., etc., etc. I then rename it as NDVI, and that's quite important. You'll see why at the later stage. And then I display it. I know already that the minimum is -2. Okay, the minimum is -2, and the maximum is 1. Maximum is 1 if I apply my scaling factors. And then my color scheme. Okay, this is this color. I just copied this color scheme. There's a lot of colors in this. We may have to simplify it, but let's go for it. So I just use that color scheme, and it will be presented within NDVI. So again, nothing out of the ordinary, straightforward. Okay, so I generate a single image or a reduced image, a mean image of my NDVI for my region of interest for that period. Yeah, so and it's, as I said, it's a scaled value, so it's actual numbers. Okay, so that's my y variable done, and that's how it looks. That's how it looks. Okay, that's my y variable done. Happy with that? Nothing different, nothing strange. Let's have a look at my inspector. Let's click on some value or some location and see what the NDVI generates. Okay, so there's now population there. There's an NDVI of 0.3, that location. So let's click on something like here. Click on that value. There's an NDVI of 0.43. Let's click there. There's an NDVI of, let's have a look. Some point it's going to give it to us now. Just wait. 0.32. Okay, so if I use my inspector and I click on different locations within my my region of interest, it will give me the NDVI value for that particular location. And remember, this is a dryish area, so I don't expect NDVI in predominantly agriculture, so there's lots of bare soils, etc. So I don't assume NDVI values to be very high, which is exactly what's happening here. Okay, so that seems to be fairly plausible and acceptable numbers within the range of -1 to 1. So I'm happy with that. Now the question is, what are we going to use as our explanatory variables, our independent variables, the variables that we want to use to model NDVI. That's our next question that we have to now think about. Okay, so I've got a couple of ideas. And again, this is again discretion, that's up to you. Ideally, there should be logic, there should be theory, there should be a thinking behind it. You can't just plug the variables and out of thin air and say, let's include it. There must be logic behind it. There must be a reason, right? You must be able to defend it if asked. Okay. So remember, there's a methodology behind this that you have to follow. Okay. Otherwise, your result is rubbish. Otherwise, you remember that saying, rubbish in, rubbish out. Okay. So it must be well argued and founded variables. Okay, it must make sense. So obviously, for my region of interest, obviously important is temperatures. That's obviously important. So one would expect the hotter it is, the lower the NDVI would be, meaning the less mass and less healthy the vegetation. So that makes sense. Makes sense. Okay, so I'm going to include temperatures. Okay, so I'm going to include temperatures. And for that, I'm going to use this particular data set. Now, there's again a couple of data sets that you can use. That's totally up to your discretion. Let's use the MODIS data set. Okay, so let's go and have a look and see what that data set looks like. So let's have a look and see. Okay, normal, go to Google Earth, go to the data sets, paste it in, and there it is. Terra land surface temperatures. Land surface temperatures. There it is, 2000 to 2024. So it's within our time frame. It's got LS day, 1 kilometer. It's in units, land day, land surface temperatures. There's the minimum, Kelvin. There is the minimum and maximum, and again, scaling factor, okay, which we have to apply. There's the color schemes, blah, 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 blah. Okay, point noted. Okay, so same as previously, I select my data set. I select a band because it's multiple bands. There's more than one band. There's also that band. So there's multiple bands in here. So I include my band. My period of analysis, same as the previous one. I clip it. Okay, then I scale it. Now, in my case, I'm not actually scaling it with 0.02. I'm actually scaling it with 0.002. Okay, because that brings me to the correct number. Okay, and I'll show you now. Okay, so I'm actually using 0. So there's some discretion that you have to use here. Okay, but in my case, using 0.0. And again, I rename it, and I'll show you why. And oops, I need to change these numbers. These numbers are now the modified and not the actual. So it's actually minus 10. Let's want to get minus 10, minus 2, and it will get to 40 degrees, but let's make it 50. Okay, blue, green, and red. Temperature, I'm going to display it. See how that looks. This probably will look terrible simply because my minimum and maximum numbers were totally out of sync. Because I didn't amend it after I've added the scaling factor. Okay, but anyway, yeah, so it will look out of sync. But anyway, let's click my inspector, click on a location, and you'll see the temperatures. There we go, temperatures 30 degrees. Now you see if I use 0.02, like what they suggest here, 0.02, then it will be 300 degrees. Now that's totally impossible. I won't be sitting here speaking to you if it was 300 degrees. No air conditioner is going to help. I would be dead. So that's why I said I made another 0 there so that the temperature becomes reasonable, logical, makes sense. So that's why I amended it, okay? So please understand it. Now it will, just the color scheme will look terrible because, as I said, it will only be green, which is this one, which is in the middle of the previous minimum maximum. So that's why it would look awful. Okay, you can copy and paste. Where is it now? You can copy and paste these color schemes. If you want to, you can copy it and we can paste it in there. Let's paste it in there. And that should give a better color scheme. Okay, I'm not going to run it now. Let's go through the whole thing. And remember to save every time you make a change. Okay, so that's my first variable, my first explanatory variable. Okay, that's my first explanatory variable. And remember, I add false here, meaning it won't automatically display. It will only display if selected, you see? It won't automatically display. Sorry, supply. What supply? Display. Okay, so that's my first explanatory variable, independent variable. What's my second one? Now you can stop there. That's single equation. You don't have to continue, but let's continue for the sake of it. So the next one is rain. Now, obviously, rain is very important because rain improves the vegetation health and mass. So we want to understand what the rain is. So obviously, temperature is important when it comes to vegetation. And rain is important when it comes to vegetation. You see, there's a logic behind these things. You have to argue it. Okay. So for this one, I'm using the TerraClimate one. Okay. So let's have a look how that looks. TerraClimate one. Let's go there. Go to my search. Go and paste it in. And let's see what it looks like. TerraClimate. And there it goes. In my time frames, there's my bands. My participation, there's no scaling factor for participation, which is rain, which is good, etc., etc. And there's the color schemes. Okay, so same thing. I select my image and I select the band, my data set, sorry. I select the band, my time frame, which is the same as previously. I clip it, I generate a year using a median. What did I do this one? This one a mean. See, ideally you want to be consistent. Mean for everybody or median for everybody. We'll have to have a look. I rename it as rain. Minimum 0, maximum 30. Can't rain less than 0. And the chances that we're going to get more than 30 millimeters is because it's millimeters. Let's have a look and see PR participation. Millimeters, yeah, millimeters. Is almost nothing. And there's my color schemes. And again, false. Let's have a look at rain. There, I've had it previously. That one, 14 millimeters of rain. Remember, that's a median rainfall for that location um, over that period of time. Let's have a look this side here. Let's click there. What that does, that looks like rain. Okay, so it has a NDVI of 0.23, maximum temperatures of 30, rain of 14.5. So that's my second explanatory variable. So I've got NDVI as my dependent variable, or the one that I want to model. My first independent or explanatory variable is land temperatures. My second one is rain. My third one is population. And I brought population in there because the more people, one would assume the less healthy the vegetation because there's more urban structures and so forth and so forth and so forth. So I included population, and then the last one I've included was elevation, because one would assume that the higher the elevation is, the cooler it will be, the more rainy it will be, the um, better the vegetation would be, also the less human involvement there would be, etc. So in my mind, these things make a lot of sense. World Pop is also image collection. I use population, the dates, clip, etc., etc. And then the elevation is only for the image as a single. So all of the variables are image collections, i.e. multiple images, except the elevation, which is a single image. That's why it's called a just an image. So you'll see there's no dates, etc., etc. I think it was taken in. I can't. Let's have a look and see when it was taken. What was the date for this? Okay, so let's have a look and see. It was Let's have a look here. It was in 2000. So it's a while ago, but I mean, really, would things have changed that much from come on, from an elevation point of view? I doubt it. And it's got the band, we select it, etc. And you see, also important is we rename all of our images into a specific name. So NDVI, we renamed as NDVI in capital. And I use capital letters simply because of the fact that it's a Y variable. Okay, so as I said, it's important to rename the variables. And the reason why we want to rename the variables, and again, you can rename it whenever, but as I said, keep it straight, keep it simple. And I said, I've put my depend my dependent variable in capital letters, and then my independent variables, um, temperature, rain, population, I put all in small letters. So once we've selected all our variables and we displayed all our variables, etc., and we're happy with it, they all are fine. You can see there they all are: rain, population, and elevation. There's my variables. NDVI is my dependent variable, temperature, rain, population, elevation is my explanatory variables. 1, 2, 3, 4 explanatory variables, 1 dependent variable. Okay, so now I've got it. Now the first thing that you have to do now is to combine these into one image. Okay, we're going to combine them into one image. And you can see this is where we include the names of it. Remember, that's where we renamed it. That's what so the renamed variables we include here. NDVI, temperature, rain, population, and elevation. So there's and we expressed it from dependent to independent. Dependent to independent. So NDVI is my dependent variable, temperature, rain, population, elevation is my explanatory independent variables. And then I just display this based on the NDVI. Okay, you don't have to do this part, but if you're going to display this combined image, you can display it based on my NDVI. So I'm going to display it based on this one, not on this one, but you can change it. So I can display this combined image on any of these variables, but I said I just use the NDVI as my based on what I'm going to display it. Okay, so that's very important. I'm taking all of this, what I've done so far, and I add it into one image. That's image. And I display this image based on the NDVI image or variable. But you can put in there temperatures, rain calculation, any of them you can put in there. Okay, so that's just how I'm going to display it. But now I've got a single image with all these variables included, with all these images included. Okay, and I call it combined. And again, that is totally up to you. You can call it whatever. Now, the next thing that we have to do is we have to create, because remember, all of these images so far, they all have different resolutions. So this is a 30 meter. Remember, the other one was 1,000 meters, and it's 100 meters. So they all have different resolutions, i.e. pixel sizes. Okay, so what we want to do is we're going to create locations, or we want to create point locations, and then we want to add the data of each of these variables to each point location. So we want to create point locations, random point locations. That's why we have random here. So we're going to create random point locations throughout my region of interest, and then we're going to add, or we're going to generate the data for all 5 of these variables and add it to each location. Okay, so in this case, I'm going to generate 10,000 locations within my region of interest from this combined image, From this combined image, there we see, I'm going to generate 10,000 pixels, number of pixels, 10,000. That's totally up to you again. My scale, because it's 10,000, it's very huge. So a 30 scale or 100 scale is not going to work. So I make my scale 1,000. But again, that's up to you. And it's going to be totally random. And I'm going to then add this 1,000 points. I'm going to display it. Let's quickly show you. And there it is, the sample. It's called sample. You see, there's the 100 locations or 1,000 random locations. If I go in, let's go in again. Let's zoom a little bit in. Let's take this out, all these ones out. We leave NDVI. Okay, so while that is, you see there is the random points. Okay, there's the random points. Okay, and then for each of these random points, we're going to add the data, the information. So each random point will then have an NDVI value, it will have a temperature value, it will have a rain value, it will have a population value, and it will have an elevation value based on the images, those mean median images. Okay, so that's what we're doing next one. Okay, we're creating that 10,000 random points, and then we generate the data for those 10,000, generate 10,000 points. Now, as I said, that's totally up to you. That's totally up to you. Okay, so let me pause here for now for this particular video, because the next one is actually doing the random forest. But this is absolutely important in terms of doing the prep work, the get go work, so to speak, getting going with random forest. You need all this work to be done. Okay, otherwise you're not going to work. Okay, so load my region of interest, load my dependent variable, load my dependent variables, create one image with all the variables, and then create a random random number of points where we then generate the data for each point. Okay, so that's important that we've done. Okay, so let's park there for now. Let's pause. We'll continue with this in our follow-up video, which will be around the corner. Thank you again for joining me for this episode, this part of the journey. I really appreciate your attendance and support. Please remember to like, subscribe, share the video. The more the merrier. We would like to get as much feedback as possible. We'll try to make it as interesting, as informative as possible. But yeah, thank you very much for everything. And we shall be back, as they say. And as I always conclude, I'll see you on the other side.